And I just wanted to remind that in Dijkstra's algorithm, we basically found out the least cost path. And the next algorithm that we're going to talk about is Bellman-Ford. And Bellman-Ford is slightly different. Here, this is what we would call the distance vector algorithm. And the distance vector means you tell your neighbors about your distance to the whole world. Right? Link state, you tell the world about your neighbors. Distance vector means you tell the neighbors about the world. So basically everyone exchanges their complete table with everybody, for all of their neighbors. Everybody exchanges their complete table with all of their neighbors. Neighbors only, not everybody else. And then they find out if there is a shorter path exists. So first way to do that is to just take an example of a 3-node network where everybody is a neighbor of everybody else. So here actually, I mean, in this example actually the world is equal to the neighbors, but it becomes clearer as to how these things work. So basically we start here, there are 3 nodes x, y and z. The complete table for x is that my cost to x is 0, cost to y is 2, cost to z is 7, and I don't know what is y's cost to x, y, z, and I don't know what is z's cost to x, y, z. Similarly, y says that my cost to myself is 0, to x it is 2, to z it is 1, and I don't know their cost. And z has this table. The whole table is sent to the neighbors. So x sends its table to y and z, y sends its table to x and z, and g sends the whole table to x and y. Now really, since the rest of the table is infinity, that really doesn't matter. This is the row that makes a difference. So when that row arrives here, then x does the recalculation. It does recalculation, it finds out that its cost to z is actually not 7, it is 3. Why? Because it can go to y for the cost of 2 and y can go to z for the cost of 1, and therefore we can go to z cost of 3, which is better than 7 before. Similarly, y does the calculation. It gets 0, 2, 7, 2, 0, 1 and 7, 1, 0. It does the calculation and sees, can I reach x any cheaper via z? Finds out no. Can I reach g any cheaper via x? And finds out no. So it doesn't change anything. And z does the calculation. It was 7, 1, 0. By that calculation it comes out with 3, 1, 0. It sees that I can reach x via y much cheaper than I was going to go directly, and therefore the cost is 3, 1, 0. So the rule is anytime your table changes, you tell the neighbors again. So these two will tell their neighbors that my table has changed, and x will tell y and z will tell y and x. So now when x gets this new table from z, from y it doesn't get any new information, from z it got a new information 3, 1, 0, it double checks whether any way faster to go to y and z, and it doesn't change at all. Similarly, z actually does the same calculation, nothing changes, and y does the same calculation, nothing changes. Since nothing changes, the program ends. Nobody sends anything more, and as a result, basically this is the shortest path. Yeah.
Is there a difference in efficiency between Bellman-Ford and Dijkstra?
Oh yeah. So we will come back to that when we talk about OSPF versus RIP and why Dijkstra is better. Well, you asked a different question, I answered a different question. You said inefficiency. So in calculating whether one requires less instructions than the other. Well, actually the problem with the with the whole distance vector is more about how long does it take to settle. And it could take a lot of cycles before you would settle, and that's the problem. All right. So everybody understands what's happening here, that you tell your whole table, you send your whole table to your neighbors, and the neighbors recalculate based upon this new knowledge. If there is any change, they tell their neighbors, and so on and so forth. This continues until there is no more change. So to do this, one way to do is write on the diagram, and that is actually probably easier way. You bring a pencil and a paper, and then you start writing the numbers and erasing the numbers and writing it again. So let's start with this diagram. This diagram shows I want to get all the paths from U. Just arbitrarily selected that we want to get all the paths from U, and the linked paths are given, but we don't know really how much is the cost, and the cost is given in these circles. So the cost to go from U to V, right now we don't know, that's why we put infinity. To go from U to W, it's infinity. To U to Z is infinity. U to Y is infinity. U to X is infinity. Simply because U just came up. So U doesn't know the cost, but it knows the link cost. Since it knows the link cost, it says, well, since I know the cost to W is 5, cost to V is 2, and cost to X is 1, I at least know the cost to those 3 nodes. So it erases those infinities and puts there 1, 2, and 5. Yeah.
Can you explain the difference between link cost and actual cost again?
Link cost and actual cost.
Like link cost and the infinities.
And what?
And the infinities there. Like, can you
Infinity?
explain the difference between them? Like the difference between like the 1 and the infinity, or the 2 and the infinity.
Oh, okay. Infinity is simply a notation here, don't know.
Right, but that's, what kind of cost is that? Like, what's that called, cost-wise?
What is that don't know cost is called?
Sure. Like, the link cost is the 1, 2, and 3, right?
Those are the link cost, and these are all the link cost right here. But this is, one is the cost from U to X. This is the path cost.
So what's the difference between link cost and path cost?
Okay, what is the difference between link cost? Okay, so here thing. The cost of this link is 1/2, right? So this link is 2, but the path cost from U to W, U to Z is 1 plus 1 plus 2 is 4. So the path cost is 4, but the link cost is you have to ask for each link.
But why is it not infinity? Because you said the cost from...
Oh, this is the path cost. Sorry, these are the path cost. These infinities are the path cost.
So if I wanted the path cost from in B, if I wanted the path cost from U to Z, it would be infinity.
At this point, it is infinity. Path cost means we don't know. But by the end of the diagram, the path cost is 4.
Okay.
Yeah, okay. So the numbers which are next to the link are the link cost. The numbers which are inside the circle are the path costs. In particular, the path cost from U, not from anywhere, from U, this node U. So this number, for example, go to the, and we will go from this diagram A, B, C, D. By the time we are done with this algorithm, we know the path cost to every node. So the path cost to V is 2, path cost to W is 3, path cost to Z is 4, path cost to Y is 2, and path cost to X is 1. So these are the numbers, but at this point we don't know those numbers. Is that clear? What the numbers are? Now, how do we get from there to here? So what we do is we go one hop at a time. So right now this is the 0 hop cost. Basically, if I didn't want to go anywhere, this is how much it will cost. If I want to get to Z in 0 hops, then I can't get there, period. But now if I want to go in 1 hop, then I can get to 3 nodes. And the 1 hop cost is 2, 5, and 1. So the paths are 1 hop and the costs are given. Now we go to 2 hops. So now we want to be able to 2 hops. If you want to be able to go to 2 hops, then the cost for W is not 5, it's 4. Why 4? Because in 2 hops you can go like this, 1 plus 3, 4. Why are people leaving early?
We have a presentation.
Eh?
A presentation in Green Hall.
Okay, I don't know. What is the presentation about?
It's electrical engineering. It's PX.
I see. Okay.
Is that being green? No.
All right. So in one, this is 0 half picture. This is 1 half picture. This is 2 half picture. In 2 halves, W can be reached with cost of 4 because we can go like that. Y can be reached with a cost of 2. We can go like that. And Z can be reached with 2 halves can be reached. How can it be reached in 2 halves? By this path, W. So it will be 10. All right. Now if we go 3 halves, if you go 3 halves, then this number can be changed because then we can come 1, 1, 1, 1, and it is 3. And this number will change because it is 1, 1, 1, 2, it is 4. Right? So the way this algorithm works is you first calculate all 0 half paths, then you calculate all 1 half paths, then you calculate all 2 halves paths, 3 half paths, and so on and so forth. You just keep increasing the area that you are covering in your network.
How would the algorithm look like?
Yeah, so the tabular form. So we do it in the tabular form as follows, that we write down 0 half, 1 half, 2 half, 3 half, 4 half, these are the rows, and for the 0 half, everything is everything has 2 columns. First, what is the cost and what is the path. So the cost is infinity, the path is not known for all of these. 0 half. For 1 half, then we look at the diagram and we say for 1 half where can we reach? We can reach V, W, and X. So we write down the cost 2, 5, and 1, and we write down the path UV, UW, UX. Everything else is unknown. Right? Then we say now we are allowed to have 1 more half to reach the world. And so if we were to go 1 more half from whatever we basically know, U, V, and now right now we know U, V, W, and X. So basically 1 more half from V is W, and that would be cost is 5, that doesn't help. 1 more half from X is W and Y. W can be reached at 4, so that changes number to 4. So we change that to 4 and we say that can be reached by U, X, W. And similarly we try out what are 1 half away from V. So from 1 half away from V is X and W, those are the only 2 things, so that doesn't help. What is 1 half away from X is V, W, and Y. So those 3 numbers we calculate. For V we get the number 3, for W we get number 4, for Y we get number 2, and since those numbers are smaller we put 2 and 4. Alright, and then we see who are the neighbors of W. W has neighbor V, X, Y, and Z. For each of them we calculate the cost and see if any cost decreases. The only cost that will decrease is Z. Z becomes 10 instead of infinity. So what you do is you take 1 half away from everybody that you knew before, basically, right? So this gives you these numbers, and the red numbers are simply the new numbers which change. If they didn't change, then we just leave them alone. And so we get the new half, a new path, and the new cost. Then we want to do 3 halves, right? So for 3 halves we do the same thing. We go to all the people who are 2 halves away, and we go 1 half from there. So this is the node. W is 2 half away. So we see from W we can reach V, X, Y, and Z. W's cost is 4, and therefore V's cost is 7, X cost is 4 plus 3, 7, Y's cost is 4 plus 1, 5, and Z's cost is 4 plus 5, 9. Alright. So if anything changes, we write that down, and then we go to what else is 2 halves away is Y. So we see who are the neighbors of Y. X, Y, W and Z, and then we calculate their new cost, and it turns out that only Z's cost will go down, that becomes 4. Alright, in fact W cost will also go down because it becomes 3 if you go by Y. So you put that UXYW and UXYZ. Alright. Then when you go to 4 hops, you look at the nodes which are 3 hops away, which is Y, and then see if you can reach anywhere faster. So from Y you can reach X, W and Z, you calculate the cost, nothing changes, so you are done. So you go first, who can be reached 1 hop, and then from 1 hop how can we reach 2 hops, from 2 hops how can we reach 3 hops, and you just look at the nodes which are 2 hops away to find 3 hop paths, from 3 hops you find 4 hop paths. Okay. So once you write this table down, then at the end you have these are the cost and these are the paths. Alright, now here's the thing, the table is not in the book. So if you don't understand it now, please ask now, because the book simply gives this example and then gives all the formulas. It may be difficult to apply them. So these are the things. You write down first all infinity, then go everything that is 1 hop away. Then you look at all these nodes which are 1 hop away to find out 2 hop paths, everything else from there. So you go to V, find out which are 1 hop away from V, W, X. Then who are 1 hop away from W? V, X, Y and Z. Who is 1 hop away from X? V, W, Y. So you calculate 2 hop paths to those nodes, right? And if anything lowers, changes, you put that number here in 2 hop. Then you look at the 2 hop paths and nodes which are these, which is V, W and Z, W and Y, and then see if you can find the 3 hop paths. And so on. Does everybody feel comfortable going row by row? And you may have to erase a few times. For example, here you might have written 9 first while coming by this method, and then you say no, I have 4 or something. So 10, you might, I wrote 4 here, but that is the lowest you can do. It is quite possible that you might have come some other method and first you came from 10 to 9 and then to 9 to 4. Yeah.
Should Bellman-Ford and Dijkstra's give you the same answer?
Answer will come out the same. Yeah.
This table is for you.
This family?
This table is for you.
For you only, right? Yeah. For the node U. If I ask you to do the same thing for node X, you have to start all over again.
This is the shortest distance from single source, right? To all nodes.
Yeah, from this node to all the nodes. From that node to all the nodes. So every node has to do this kind of calculation by itself. All right, that brings us to the end of this summary, this part, which is calculation. So this is basically algorithms, and you have to distinguish between algorithms and protocols. So we haven't discussed the routing protocols. We discussed the forwarding protocols, which was IP. We discussed the routing algorithms, which is Bellman-Ford and Dijkstra. Now the next module would be routing protocols. All right, but before we get there, here is the summary of the routing algorithms. 4 key points. Distance vector is distance. So you have to remember what is distance vector. Distance vector, is that I send a big vector of all the distances to the whole world to all my neighbors, few people. Link state is that I send the information about my connections to my neighbors to the whole world. All right. And Dijkstra is link state, and Bellman-Ford is distance vector. Here are the section numbers and so on and so forth. All right, 4.53, even though you read the whole 4.5, 4.53 is not covered. That is in the next module. Yeah.
So for Bellman-Ford, at the end of the algorithm, each node knows the next hop to get to a certain node.
So basically you get this whole thing. You not only know the next hop, you know the whole path. So with Bellman-Ford here, when you know the whole path, so for example, U knows that to get to W, I will go to X. but it also knows that from there it will go to Y and W.
How is that path stored?
Yeah, it is not stored. Basically, once you do the calculation, then you get back the same table, which was very similar to you saw the routing table in the book. I mean, you saw the routing table everywhere else. I mean, you saw the routing table in NL, or you saw the routing table in our routing table exercise, where you just remember the next hop. So you don't store the whole thing, but you do the calculation.
Still not sure how do you use Dijkstra differently from Bellman-Ford. They both give you the same result, right?
Yeah, they give you the same result.
No to every other, right?
Yeah, they give the same result.
So why is the usage different?
Oh, basically the information that is exchanged is different. To calculate, the thing is, okay. So what we did here was we used the table method, assuming that we know that the cost is from W to Z is 5. How does that cost comes to U?
So it's the cost from U to W plus the cost from W.
No, all this thing, basically the way it comes in Bellman-Ford is that the W sends the whole table to U. In Dijkstra, W sends only 3 numbers to U. See, so the difference is in what information is exchanged with whom, which is not shown in this table.
Isn't W calculated, like U calculated everything in the links?
Yeah, and the way it is done is more like this, where you keep getting piece by piece information, and as you get a new piece, you recalculate the whole thing.
Right,
So you end up with the final table. Huh?
So why is it different from getting just the single vectors from the neighbors?
Oh, okay. All right. So the question is, why is it better to have a small vectors from the whole world or to the whole world by a large vector with small? That is in the next module. I think the same question was asked here by somebody. I think you asked about the efficiency, but the issue is not efficiency; it's the convergence speed. One is better in convergence than the other. Okay, I think we'll stop right there. Next time we will go into the. But there is one more change I have done, and somebody asked me a question about this module here. I think let me see. I made a change. I want to make sure that you make note of that change. Hold on, please. Okay, this one. In your handout, I had told you that ATM is not covered, and therefore these sections do not need to be read. 4.1.2, 4.2.1 do not need to be read, and R4, R5, R6 do not need to be done. Everything else needs to be done. So, so this is, you mean on the website? No, it's not on the website yet. It might be. Today, I just changed it today before coming to the class.